Hello, everybody. We will talk about the transition elements as the next part of the periodic table. So in the previous videos, we talked about these two columns and these six columns, and we discussed them in sort of details. And we mentioned that they have kind of common properties because of the way or the subshells that are being filled. So we knew that these fill the S subshell, and these fill the P subshell. And because these elements here fill the D subshell, they have different properties, and they're kind of have similar properties that can be predicted based on their location in the periodic table, and that's why we talk about them separately. And we call them the transition elements, and they consist of 4 rows, as you see here, and each one of them is called as a group of transition elements. So this is the first transition element, this is the second transition element, third and fourth transition elements. And what we will do in this video is we will talk about the electronic configuration of these elements, and we will based on this configuration we will talk about the properties that are characteristic to the transition elements. So to talk about the transition elements, we mean by them that these are the elements that have partially filled the subshell, and that's why this definition is kind of important, because sometimes people do not consider this column, elements of this column, as transition elements like zinc, cadmium, and mercury, because they have filled the subshell. It's not partially filled, it's totally filled subshell. However, if you have zinc ions, cadmium ions, or mercury ions, these will be considered as transition ions, because they have unfilled the subshell. And the same here, scandium and deuterium are transition elements, but scandium ions and deuterium ions will have empty d subshell, and that's why they're not going to be considered as transition ions. Anyways, to talk about the electronic configuration, this is how the transition elements are, or the electron configuration of the transition elements. You'd see that this has 4s filled subshells, and then it's filling the d subshell 1, 2, 3, and the same here, s and d, same here, s. But we have here F in between the S and D, but again we have the D subshells are being filled here one by one. But there are some kind of elements that have configuration that's not as expected. So for instance, we see here chromium has a different color here, because the configuration goes as 4s2 3d1, 4s2 3d2, 4s2 3d3, then for S1 3d5, which is not expected actually, because we would expect this to be for S2 3d4. But what happens is that this configuration is more stable, and the energy of the atom in with this configuration is less than for S2 3d4. And what it does, it fills the orbital in the S subshell with 1 electron, and the 5 orbitals in the D subshell with 5 electrons. So you have 6 orbitals with 1 electron each, and instead of having the 6, one of them is filled with 2, and 4 filled with 1, and 1 empty. So this how it gets more stable. The same here, this is for S1, it's not 2, this is a mistake in the figure. So this should be for S1 3d10. Again, you have the 10 electrons filling the D subshell, and the S subshell is filled only with 1 electron. So again, this is a more stable state. You'd see the same here for molybdenum, and you see the same here for gold. Some others have different configuration, which is not very expected. Anyways, this is something to keep in mind. Going to the properties of the transition elements, we would first like to take a look at the metallic properties. And again, the metallic properties are governed by the electrons that form the electron cloud, which is responsible for the metallic bonding. And we mentioned before for the lithium, sodium, potassium elements, which are the group 1 elements, is that the melting point and if the melting point gets smaller or less as you go down, which means that the more or the higher molecular weight atoms have less boiling point. And we said that this is because the metallic bonding gets weaker as the electron or the radius of the atom gets bigger. Here we would see that the melting points are very high. They are almost all of them are more than 1000, except for zinc. And this is because you have 10 electrons or 10 locations for electrons in the d subshell. And this makes the electron cloud way more stronger than it is with only one electron. So it's the chromium here, you'd find that it has a lot of electrons from iron, cobalt, nickel. So the melting point gets very high. This applies for all the metallic properties and for all the mechanical properties. You'd see that these elements are, or these metals are very tough. They are very hard. They are very difficult to bend or break. And this is again because of the metallic bond that makes them very, very strong elements. One other property that is very characteristic to the transition elements is that they have colors, or the salts of these elements have colors. So for instance, here you'd see that this is cobalt nitrate, it's red, the potassium dichromate orange, potassium chromate is yellow, the nickel fluoride is turquoise, copper sulfate is blue, and potassium permanganate is purple. This is not only like this. You can find that the same transition element can have, or the salts of the same transition elements will have different colors. For instance, the manganese, if it is 3 plus, it's going to be violet. If it's 2 plus, it's going to be pale pink. Iron plus 2 is going to be pale violet. Iron plus 2 is green, and so on. So this is a very, very common property of the transition elements. And again, here for this, I'm not sure if this is going to be clear in the video, but this is the hexahydrated copper salt. If it reacts with chlorine, this is pale blue. The hexahydrated copper salt is pale blue, and it turns into green when it's cuprous chloride. So this is a very, very characteristic property for the transition elements. And again, the reason is that for these colors, the electrons in the d subshell or the orbitals have very close energies, and this is why the electron can easily get excited if some light falls on it, and this light will make the electron go to a higher orbital, and then it will lose the energy and go back to its original place and release this energy that it acquired before. And this energy that's released by the electron is in the visible region, or the wavelength is in the visible range, which makes it visible for us, and the color changes as the electron moves to a different place, and the different wavelength reflect or translated into different colors, as we see here. And that's why having 3 electrons or the manganese 3 plus will have different color than manganese 2 plus, because the electrons in this case is different from the electron in the other. One other property is that the transition elements can form what's called ligands, or complex ions. And complex ions is kind of similar to the ions that we know in the classical chemistry that we are used to. It's like sulfate, carbonate, bicarbonate, and all these ions. They're a group of elements, and they form a block that acts like a single component. So if you have sulfate reacting with other salt, it's gonna turn, or with an acid, it's gonna turn into sulfate, but it's another sulfate. But it's again, the sulfate is not broken. And we will see here there are different types of complexes. It's like cyanoferrate, hexacyanoferrate 3. You can have I'm not sure MnO4, it's potassium manganate, it's manganate, and the chromate, you'll find the cyanate. Anyway, so you'll find a lot of complexes, and the reason the transition elements can form complexes is that because it has again many electrons in the d subshell that can form bonds with other molecules or with other atoms, and this makes it able to form this complex shapes that we see here. Just to understand one last thing about the complexes, we say here some of them are octahedral, some of them are tetrahedral, some of them are square planar. This is how the ligand molecules are arranged in the 3D space. So usually these groups that are attached to the transition element are charged, and these charges are all the same, and that's why they kind of repel each other, and they try to go into places that are as far as possible from each other. And that's why sometimes in this like this case they take what's called the octahedral. It's like the iron atom is in the center of a square or a cube, and each one of these cyanide groups are located into one of the corners of the vertices of the cube. And that's why we call it the octahedral complexes. Some of them are tetrahedral. It's kind of similar to this, but instead of taking a cubic shape, it's a pyramid shape with a square base. And some of them are square planar. It's like they're arranged in space in a planar surface and taking shape something like this. Anyways, so this is what we need to know about the complexes. And then we'll talk about the variable oxidation states. And by this we mean that we have already seen this before. It's like here we see manganese 3 plus and manganese 2 plus, iron 3 plus and iron 2 plus. So it can form molecules by going interactions with different oxidation numbers. So it can be manganese 3 plus or manganese 2 plus. And to understand this, we need to again to refer to the electrons in the d subshell that have close energies, and we can find the effect of this on the ionization energies. So the first ionization energy for non-transition element will be 578 for aluminum, for instance, and then it's going to be 1800, and then 2700, and then 116,000. So it's like big jumps between each one of them and the other. So it's not easy to go from one transition from oxidation state to the other. However, here you would find that the jumps are not as big. So it's gonna be doubled and then kind of getting almost doubled and then less than doubled. So it's easy to go from one oxidation state to the other, and this makes the transition elements able to form more than one oxidation state. The figure here below, we'll see that the y-axis here is the atomic number, and this is the transition elements started from scandium, titanium, vanadium, chromium, manganese, iron, cobalt, and so on. This is the first transition elements, the first group of transition elements. This is second, this is the third. And we see here the oxidation states 1, 2, 3, 4 till 8. And by this we mean how many electrons can be removed from the atom, or what's the charge that will be on the atom when it goes into reactions. So we'll see here, for instance, scandium can be scandium 3 plus, titanium can be titanium 2 plus, or 3 plus, or 4 plus, can be any of these. Vanadium can be 2, 3, 4, 5. These are all oxidation states. Chromium will be 2, 3, 5, and 6. But 5 is not very common. That's why they put it in a white circle. Manganese can go from 2, 3, 4, 5, 6, up to 7. and so on. So this is how the oxidation states are arranged for each one of these element of the transition elements. Um, and we'd expect that these transition or the variable oxidation states will reflect on the properties of the compounds formed by the transition elements that have different oxidation states. So, for instance, when we form an oxide of the transition elements, like for manganese, we give a manganese an example because it has a wide range of transition or oxidation states. So we here see that it can form MnO, which is magnesium 2 plus, Mn2 3 plus, MnO2, which is 4 plus, then 6 plus and 7 plus. When the oxidation state is low, like for these two cases, 2 and 3, the oxide is basic. That's why it can react with like here it's magnesium fluoride, so it reacts with alkali metals. I mean the halogens. However, here for the higher oxidation states or higher oxidation numbers, it's acidic, and that's why it reacts with metals like potassium. This is potassium permanganate. So it's important for us to understand that having different oxidation states will reflect on the properties of the salts that are formed by the reaction with the transition element. We have only two just more points to cover in this video. The first is the catalytic activity, and we know that a catalyst is a material that goes into a reaction just to speed it up and come out without being part of the product. And the transition elements are very, very famous of this, and this is something that people who work on catalysis focus on while they work. They keep their eyes on the transition elements because this is the part of the periodic table that is promising for them. And we know that there are like vanadium, platinum, nickel, palladium, iron. They're all metals that are used for catalytic reasons. And the reason catalyst speeds up the reaction is that it can form bonds again for the sake of having electrons in the d subshell. These electrons are able to form bonds with other materials, so they can form bonds with the reactants and collect them on the surface, and therefore it increases the chance of seeing each other and getting into the reaction. And also the bonds that it forms with the reactants will make the other bonds weaker, and therefore it will make the chance of getting into reaction easier for the reactants. And we'll see an example here, like iron 3 plus react with iodine ions, forms iron 2 plus and iodine liquid. And the iron 2 plus reacts with the thiosulfate salts to form iron 3 plus and sulfates. So if we add these two reactions together, we'll find that these two and these two will cancel each other, and then we will end up with iodine ions reacting with thiosulfate to form iodine gas and or iodine liquid and sulfate salts. So this is how the catalysts work. The last thing is the magnetism, which is the property that is very common in transition elements. And the magnetism is, or the magnetic properties of the transition elements is a result of having electrons in the d subshell. Again, these electrons have spinning properties. Each electron rotates around its axis either clockwise or counterclockwise, and this spinning will generate magnetic force, acting like a very, very micromagnet. And we'll see that in this table, that as the electrons, the unpaired electrons in the d subshell increase, the magnetic properties increase. And this is kind of arbitrary units, which means that they were calculating the magnetic properties using another unit. The numbers were kind of not easy to understand, so they kind of divided by a factor so that the numbers will be easy to follow. So we'll see that the magnetic properties get higher as the number of unpaired electrons increase, and then gets lower with the decrease in the number of unpaired electrons in the d subshell. So this is all for this video. Again, I just want to focus or highlight this point. All the properties that we mentioned, either the color or the magnetic properties, the catalytic properties, any of these properties that we mentioned were a result of having the unpaired electrons in the d subshell. And this is something that's important to keep in mind. So I hope this is clear now, and I'll see you in the next video, inshallah. Goodbye.